Good morning, ladies and gentlemen. The title of my talk is about fatigue evaluation of light rail and structural precast panels, which are made with fiber-reinforced concrete. The purpose and intention here is to say and show that many times as structural engineers, we're asked to design a system. The design of that system can always be looked at from an ultimate limit state. What's the maximum load that it can take when I apply all of the safety factors and reduction factors? That's our mentality. But sometimes the design is governed by serviceability. We want to know if this particular structure will be able to withstand the service life that we expect from it, and design it in accordance to the criteria that, that is defined that way. So I want to say that if we switch our mentality, there are so many opportunities for us to address the problem and be able to do that. My co-authors are my two PhD students, Devansh Patel and Chichanok Plitsujai. And there are two projects I'm going to talk about. The first one is about track slabs. This goes back to 2019 when the city of Phoenix had already designed and built the yellow line, which is a single line that goes for about 28 miles, connects the northwest of Phoenix to the East Mesa community. The ridership has been wonderful, it's been great, and there were plans of extending it by going to the South Phoenix in 2023, as well as creating an extension for a major local development. By the way, a lot of you may have heard of the TSMC fabrication plant that has been built for $40 billion in the Northwest Phoenix. So definitely there is a lot of development happening in the North Phoenix area. And this extension that we're talking about was about 3 miles, about 4 kilometers or so. And the idea was the costs now were so much, and the cost overruns for these two extensions in 2023 had gone through the roof. There was not enough budget, and actually the community wanted, the business owners, they didn't want this to go forward because of the fact that the streets would be closed for more than 6 to 8 months, and they were afraid of losing the business. So the idea was, can we reduce the cost? Can we speed up the production? And I don't know what meeting it was, but somebody said, why don't we take the rebar and look at alternatives, or reduce the amount of rebar to reduce the cost? So somehow somebody mentioned fiber-reinforced concrete. After that, I was asked to go to a meeting, and I was told the situation, and I proposed that we can reduce half of the steel. Very conservatively, I said we can reduce half of the steel. They said they agreed. They wanted to did the calculations. There was $500,000 in savings that they considered, and they said, fine, go ahead. What does it take you to go to complete removal of all the rebars? And then I was skeptical of my own abilities, and I proposed that why don't we just test it for serviceability and service life. So that was the requirement for us, the proof of concept that this design with complete removal of the steel is going to work. So that's an introduction to the subject. So the objective was basically try to replace 40 centimeter thick slabs and about 2.5 meter long wide with fiber concrete, and the most important parameter for them was cost savings that they could do. And we'll talk about the cost issues as well as we go through and validate the design. This is the concern that they had. The idea that the rebar density was significantly overestimated, especially at intersections. The fact that every single rebar had to be tied together for a stray current, corrosion prevention, and at the same time you can see the traffic delays and the costs associated with that. So the original design was based on minimum reinforcement design, building up the cages, and then so we built models, we built mock-ups full size for only one rail and with minimum reinforcement, and then at the same time decided to reduce the thickness, going from 14 inches to 12 inches and using steel fibers for the reinforcement. Now, The proposed testing plan was just basically doing a side-by-side comparison and check them, and check the fatigue performance. Now, again, the main concern of deriving the cost in these issues is the fact that when we have stray current, that is basically because of the fact that the DC current that's used to provide delivery here, some of it goes through the depth, and especially if it's not your slab is not very deep and you have rebars on the slabs, then that way the current would transfer to the cathode, and then you would get basically the corrosion that would happen. So they have to have monitoring stations, the test, taking the current out and grounding everything together. This is where the problem initiates. So basically we're comparing two systems, number 4 and number 5 rebars, basically along the entire length. The length was about, so we'll talk about this. So the length of this sample was about 8 feet by 12 feet. But then the alternative is just basically just a basic mold that you're just basically pouring the fibers. We strain gauged all of the rebars to measure the state of strain in the rebar, and monitored it at the test. Of course, we go through the same preparation of the sample and casting of the concrete. And the idea of the fatigue brought us to the question of how do we design that? So we asked the questions dealing with what's the service life. They said we want it to last for minimum 45 years, okay? Then, what if we have significant ground settlement, such as, you have a main water line that would break underneath the slab. So that would create an open, and we assume that to be an 8-foot long section. So that would justify us testing the slab, not on ground, but testing it as a beam that's going to carry over a span of 8 feet. Design for the wheel load, calculate the capacity per wheel, 9,000 pounds. Look at it as double with the factor of safety, so apply 18,000 pounds as a minimum load that the slab should take from a point of view of cracking. The train runs on a schedule of 24/7 every 6 minutes, so that ends up over a period of 45 years to about 2 million cycles of loading. And that became the criteria for our testing. Of course, like everything else that I do in my work, we have to know what the material is like, so we chose, they put out the project to bid for steel fibers only, and as a part of the process, 2 companies proposed the bids, based on their own designs. One of them had 60 pounds per cubic yard, and the other one 25. It was just basically, we had no control at ASU to decide. We were just basically providing the testing and evaluation of the current state of design. We conducted the tests based on ASTM C1609, and of course that test would allow us to do several things. One of them is to calculate the load deflection results to see what is the residual strength that we get. So the 2 fiber systems clearly show the response that they have with higher fiber and the lower fiber. And when you're plotting them, what you see is this residual strength. And that's what we are banking on. In other words, my service load level should not be higher than this, even if I go for a fatigue. In other words, if I develop an ascent curve for these samples, I should always be above this. I should always be able to have this level of performance being used for the minimum load that's applied to it. But what we do is to use a closed-form mathematical model for beams, which would allow us to measure the tensile and compressive response of each sample. And once we plot the tensile response, we see that we can assume a residual tensile strength of about 0.75 megapascal, about 120 psi. That's all you need in tension. And then the other one with the lower fiber content was much lower, about 0.2, which is about 40 or 30 to 40 psi as our residual strength. This is what can be used in a serviceability-based type of a model. Then we set up the samples in our lab. So basically, this is the tray, this is the rail. The rail is in a boot, which is a rubber boot, which means that there is no bond between the rail and the load and the connection with the steel. So this is a steel bar that basically distributes the load on the entire length. So it can be treated with the stiffness of the rail. One can assume the load to be applied as a distributed, continuously distributed load. 2 support lines, and of course you see under the beam we had about 16 transducers that measured the entire deflection of the section. And then, of course, what we went through was to run the test, and here are some tests. So let me just see if I can start this video. So as the load is applied, we can see that a crack forms, the crack opens, and this is just basically the initial reinforced concrete section that very clearly shows the formation of a single crack that dominates. Now, we can, once we run the fatigue test, again we can also monitor the fatigue response, and I'm not sure if this is the fatigue test. No, this is just basically the static test. So we can see exactly where the crack is forming and how it is basically propagating through, opening up, and that would basically be allowed as the mode of failure, single crack. Now, we can plot the load, and we see that even if you put 4 LVDTs, the responses are extremely close to each other, which means that we have a very nice uniform deformation. The sample is loaded to more than about 2.5 times the design capacity, assuming that the train is filled to capacity. And then once the concrete cracks, then it just drops, but then the load can still be carried through the rail, through the entire system, and the rail now is carrying a lot of the load. And so this is a composite total effect of the load and the concrete phase. 4 LVDTs almost measuring the same response. Now, the different samples can be compared. Your original design is shown in blue, which is the reinforced concrete. Extremely stiff system. We can go up to about 220 kilonewtons, about 48 kips, and it's really stiff, less than 0.1 inch deformation. The one with only fibers is going through, first of all, your load capacity, your design level is about 10 kips. Whereas what we do is we go up to about, and the first cracking is actually extended something like even the thinner section with the less, although it's a thinner section, so there is a stiffness effect because of the depth, but then you go up to about 25, then once the fiber cracks, your crack can open up to about 0.2 inch opening or 5 millimeter opening, which can be easily repaired within a slab on ground from a routine maintenance, maybe every 10 years having a routine maintenance to calculate that. And that would put us about 3 times the capacity that we would need. Of course, what we can do is to get closer look and find out exactly when the system cracks. So the current design cracks, it's designed well because you have a factor of safety of about 1.5 on it. It cracks at about 13 to 14 kips, but then the fiber reinforced concrete goes up to more than twice that because the fibers suppress the localization. The fibers stop the cracks from forming, especially when the size of the sample is getting large. Because in the reinforced section, yes, you have the rebars, but it takes nothing for a crack to grow from this. When it forms at the bottom at the tension, it takes nothing for that crack to run from this to this. And this is just a number 6 rebar over 2 feet or so. So there is no way the load is going to be transferring to that rebar effectively. It stays in the concrete because of the stiffness and it cracks. And that crack is clearly shown in here that the response is dropped. Now, so basically the rebar is still elastic, even if you go to about 50 kips. So this is a purely elastic design, which is so expensive. Now, we can use the digital image correlation, the data to show us that with the fibers, now we're getting multiple cracks happening very close to one another. And that distributes the cracks. You have a much more uniform deformation. And this allows us to basically assume that our deflection is not going to be localized. So the potential for failure in terms of durability is much less. Although I'm not so worried about corrosion because of the humidity or salt in Phoenix, Arizona, but still these are very comforting. So we can also look at now, then we conducted the fatigue tests, and in here we're going through 2 million cycles. And as we go through these cycles, at every 50,000 cycles, without pausing the test, we collect about 100 or so cycles. So first the specimen is cracked under load, and we're doing the fatigue in a post-crack type of an environment. And that basically provides the loading that we have. And it's still, everything is still in the elastic phase, other than the concrete that can crack. But once the cracks form, you can see under the amount of the load, which is 3 times, that's the opening that you would get with the opening of the crack. So the cycles of fatigue or sinusoidal functions run at a frequency of about 4 hertz, which would mean that it would take 8 days, 8 continuous days for running the test. So it's not that difficult to simulate these in a laboratory, even on a full scale test. Now, the process of analysis is a little bit tedious because you have to get these samples of data at different intervals. So at every 100, so we call it loop 1, that's 50,000. Loop 10, that's from 500,000 to 550,000. Loop 20, from 1 million, and so forth. So from start to finish, so this is at the end. So this last one is almost at the end of 2 million cycles. And by checking the stiffness of the loading unloading at this stage versus this stage, we can actually see what is the total amount of degradation that has happened in terms of stiffness. So this figure shows, for example, the reinforced concrete section. And so we basically went up to about 500,000 cycles. And at that point, there was large enough of deformation in the section that required us to pretty much stop the test and don't go forward with the test anymore. In other words, the load was purely carried by the steel, and then the stiffness was basically suffering from that when you compare the 2 responses. So with testing, so we go with the SFRC specimen, and we see that the stiffness is pretty much rather constant for various loops. And after 2 million cycles, this is where we are. We went all the way up to about 30 kips, 125 kilonewtons, and then characterized that the section can still carry and has the stiffness to withstand the type of loads that are applied. So again, the stiffness reduction can be plotted, and we see that there is 11% reduction in the average stiffness for the reinforced concrete compared to 8% reduction in the average stiffness after 2 million cycles. Note that this stiffness is not the exact stiffness because of the nature of the test, we are also adding the constant value, which is the stiffness of the rail, into the calculations that we have. The rail is carrying the load and distributing it. When we go, now this is the final. So basically, to summarize this portion, the project was approved. They switched, and it took about almost 6 months or so to convince the contractor and the structural engineering community, and they went with that $500,000 cost savings. But at the end of a project, we've had meetings with the City of Phoenix and the Valley Metro, and the statistics are staggering because it shows exactly how many pounds of number 4 rebar and number 5 rebars were used in the original plan, because they had all of this data because of their prior experience. However, that amount of steel was replaced with almost 50%. So instead of almost 480,000 pounds, we went to 200,000 pounds of steel fiber. So more than twice reduction in the total steel. The cost of concrete was slightly lower, so 328,000 versus 281. That's because of 2-inch savings. The fact that we removed the cover itself is sufficient if we do any project with fibers, if you don't have rebar. So the added cover that we assume that it cracks, it's tremendous. Then in inspection, there is cost saving, material testing is cost saving, and when you do the calculations on a rough number, it would cost the city $3,300 per linear foot of the slab compared to $1,000 with fibers. Now, here is the final thing. At $17 million, which was the original budget, this portion of the project, when they added up, cost the city $5.4 million. So there was a $12 million cost savings, and that was simply because, not because of the material, because of the scheduling, because it could be done so much faster. For a 480-foot section, that is the standard in measurement, which is the labor cost would reduce from 21 days of labor to 11 days. Total project, instead of taking almost 8 months, 231 days, was reduced to 4 months. So almost half the time. The placing of the concrete and finishing it was not the critical path for the calculation. And that's where this $12 million comes in from all of the savings. And the labor costs definitely is shown in here in terms of the track hour that we had. So this project was very successful. On the last part of the project, they asked for a polymeric fiber. Can we change some of it with a polymeric fiber? We also were able to do a section with polymeric fibers, macrosynthetic, and that was also successful in terms of meeting all of the requirements that they had. So the fact that the owner has options, that significantly improves the choices and the costs. Now, I have another project that I wanted to mention, which uses the same thing, and this approach is for precast water tanks. How much time do I have? 5 minutes? 5 minutes. So this is a precast tunnel, precast sections which are used for environmental structures that is used heavily by Salt River Project, which is a utilities company in the city of Phoenix. The idea is in their yard they make these panels at different thicknesses, and they are used at the intersections. And just imagine that on a regular street intersection they have to take a major area, dig it up, and bring it in with huge cranes. The size of each one of these is about 6,000 kilos, 11,000 pounds, and they have to place it in. Note that they are basically tied together along. So basically you're building a box, and you have to design it for the water pressure versus soil pressure and the magnitude of the load. So here is a design of a panel or a wall which is connected at the base with another small panel, and basically water comes in from one level and the other level, and basically we have for storm management or sewer or water and such. So we did the finite element analysis to calculate the stresses and looked at the different loads for design. So this is what I'm really hoping that we can push with Committee 544 to develop designs. Use these design examples as a design case so that people can pick it up and use it. Now, of course, another project that they use in order to this, they also have projects for shotcrete with fibers because they only get a week to 10 days when they drained all the canals in the region in the February, and you only have a very short time to design them. Corrosion is a major problem with many of our street bridges because of the fact that it's hot and the water in the canals that are open, they evaporate so easy. So the experimental plan to make about 16 panels to see if we can develop a hybrid system. Here is basically how much of the rebars can you reduce. So I'm going to go through these fast because this is exactly the same methodology. Can we replace one layer or two layers of rebar that is used for these sections from structural calculations based on shear requirement or structural requirement? We just basically put together a slab and then test it. Also, can you replace the loading of the rebar going from 12-inch on center spacing to 6-inch? So definitely the thickness as well as the spacing can have play a role. But the labor involved in knowing what project needs what, how to dominate it, how to calculate it becomes quite important. So the process of casting and filling, standard about the 16. These panels are put in there for lifting of it. So you know, if you know the weight, you can easily calculate what is the bending moment that the section should take for handling. These are some of the stuff. So we used our same exact equipment, except that this time we made the structure as a beam, then put these bottle jacks underneath it to support it and provide the support for transfer of the load. So we're switching the loading configuration from elastic to indeterminate structure. And so 3 different sets of testing and a significant amount of instrumentation to be able to measure the crack patterns. Similar, different types of fibers, but these are all polymeric type fiber at this stage. because we wanted to reduce the potential for any kind of a corrosion of the rebar. And then, of course, we tested full-scale sections and calculate the load and the residual value with different fibers. So the fibers are low amount to a point that we get strain softening, but you can still do the fatigue test on them with the low cycle to calculate the stiffness and run the fatigue model, simulate the response of the full-scale structural sections, calculate the material properties, and use them in our design. So the discussion of these results basically shows how we can design these systems. But the more important thing is the nature of cracking that occurs when you go from one level of restraint to higher level of restraint remains pretty the same. We get the same pattern. So as long as you have about every 3 or 4 feet, you have some type of a support or some type of a bolt to connect these, you basically get a significant amount of post-crack ductility. And this is the strain hardening that we get because that single rebar, small rebar that we have adds to the benefit. What if we go with the standard design? So this is the reinforced concrete standard design of a section, which basically it's 6 inches. We get punching shear. So at small thin slabs, 6-inch thick slabs, 150 millimeter, you get punching shear. But then with the fibers, because of the load carrying capacity of the fibers, we get the fan crack, which increases the capacity, first crack capacity. So comparing this gray with the light green color, you see the first crack and then the ductility increases. This one stops at the punching shear, this one continues. You decrease the spacing of the rebar, now you can go up to as much as you want for that 6 inches. One more. So basically the fatigue test, again, we provide service life characteristics. How much does it perform after you load it, crack it, and then go through the fatigue cycles. And I should stop here, but I just had the videos, and basically the conclusions is just, I tried to go through all the conclusions throughout my discussion.